we have learned that ketones are actually acidic at the alpha position, and the pKa roughly of that alpha position, or the acid strength in terms of pKa, is 20. So the pKa is 20 of an alpha hydrogen on a ketone. Therefore, a suitable base such as LDA or an amide ion in general can deprotonate that position to form the corresponding alpha carbanion, which can resonate to the corresponding enolate. So let's draw the structure of ketones in general. So something like that, ketones with an alpha hydrogen. So the acidity of this alpha hydrogen or alpha position is 20. So pKa here is 20. You can draw the conjugate base, the alpha carbanion. You can stabilize it by resonance as well. What about esters? Let's draw the structure of esters. So something like this. This is a general structure for esters with an alpha hydrogen. The pKa here is higher, 25. We will see why. We will draw the conjugate base and we will try to stabilize that by resonance, and we will see the difference in stability of that alpha carbanion or enolate of esters compared with that of ketones. Now, for amides, the pKa is about 30. Now, if we take or draw the carbanion of esters, we would get this. So this is the alpha carbanion. Obviously that carbon is the alpha position. So this is the alpha carbanion of esters. We can stabilize this by resonance as usual in exactly the same manner that we did before on the corresponding intermediates of ketones to make the corresponding enolates. So this is the corresponding enolate of an ester, which results by deprotonation at the alpha position. Now, so far, this is not different, okay, from that of ketones. But if you look here in esters, okay, there is oxygen. This oxygen has obviously two lone pairs, and one of them can be used to make another resonance. So we take one of the lone pairs, you make a double bond here, and now you break that carbon-carbon double bond, and you release electrons back on the alpha position. And we would get another resonance form where there is now a lone pair on the alpha carbon. You see, this is actually localization of electrons on the alpha position. This is delocalization. Yeah, so we can specify that. This is delocalization of electrons, and of course delocalization results in stabilization of the conjugate base. So this helps delocalize, this electron movement helps delocalize, of course, electrons and thus the charge, and it helps stabilize the enolates. And that's exactly why enolates are stable, because of this resonance stabilization. Now, if oxygen donates electrons, as it does, because it's an electron donating group by resonance, not only that, of course, it's also an electron withdrawing group by inductive effect. If it does donate by resonance, okay, then we get a resonance form of that type. You see, this is now considered localization of electrons on the alpha position. This is delocalization or spreading or spread of the charge of electrons, or spread or delocalization of electrons. Here it's the opposite actually. So this is now described as localization. It is localization of the negative charge over the electrons on the alpha position. That's where that's like the center of the enolate. That's really our center point of attention or focus, if you like. So it's a localization of electrons or charge. Now localization results in destabilization as opposed to stabilization, which is the consequence of delocalization here. Of course, delocalization, again, results in stabilization of the corresponding conjugate base. So there is delocalization, that's usual, that's normal, just like ketones. But here also, there is localization, which destabilize the conjugate base or the enolate a little bit. Now this element of destabilization results in lower acidity of esters. So esters, of course, here are lower in acidity, okay, than ketones. That's because the corresponding enolate, not only it is stabilized by resonance as usual, but it is also destabilized by donation by oxygen, because oxygen has 2 lone pairs, so it is an electron donating group by resonance. So we can describe OR again as EDG by resonance. So this enolate therefore is less stable. Of course, when we say less stable, that's in comparison with the enolate of ketones. So this is exactly why esters are actually less acidic than ketone at the alpha position, because of the relative less stability of the enolate or the conjugate base. That's because of resonance donation by oxygen, because this is an electron donating group by resonance.